Move on to chapter 11, feedback. We're slightly behind, but we're not so much. So we'll be able to cover most of the stuff that we want to cover in this class, which is good. Sorry that I missed one class while I was sick, but hopefully we'll recover everything, most of it. So today we're going to start talking about chapter 11, feedback. So feedback is, I'll try to cover this contents in 2 to 3 lectures, most likely 3 lectures. So it'll be one after the break. So we're gonna have a break very soon. Next week is break. I am also not here during the break. So if you have questions, you won't go to my office because I won't be there. I have to travel to a meeting. Email me. Okay, so I'll try to answer your questions by email. And feedback is a very important stuff in everything. As if you guys take E420, that's the controls class. In that class, you basically learn about the principle, the theory about feedback control. You do like Laplace transformation, you do all this time domain, frequency domain analysis, all that stuff. But they don't talk at all how you realize it. Mathematically, yes, it can be done, but in real life, how you do it. So this is what we are doing here. So we're going to spend 2 to 3 lectures to learn how we analyze feedback in terms of from the circuit point of view, and also we'll see how we can build a feedback circuit using components, using MOSFET or BJT devices. Mostly we're going to use MOSFETs as an example in this class. So if we draw a basic mathematical like a representation, and you will see that this is, oops, okay. This is very similar to what you learn in controls class. So you have in the middle, A is amplifier, and the bottom beta is a feedback. So you can see the feedback is taken from the output and it feeds back to the input side. And on the input side, you summarize the actual signal input and the feedback. So the output of that little summation symbol, the output of that is the difference between your signal input and your feedback. So if we write the expressions on this circuit, you can write it very easily. We can write, so suppose the gain of that block, the gain block is A, and the beta is the gain of the feedback block. So what we write is this. We write XO is equal to A times XI. That's the gain because the gain is A, so output XO is A times XI. And on the bottom block, it's going to the left. So we can write the output, the feedback, XF equal to beta times XO. So XO is the input, beta is the gain. And now we can also write the difference between XS and XF, which is XI equal to XS minus XF. So if we plug in XF in this circuit, we get XS minus XF is beta times XO. And we also know that XO equal to A times XI, so we can get beta A times XI. Or in other case, maybe we can do it the other way instead. Let me do it the other way instead. So here we have XI. Then we can plug in XI will be XO divided by A from this equation here. And if this equal to XS minus beta times XO. So we multiply A on both sides. We have XO equal to A XS minus beta A times XO. So we have XO 1 plus beta A equal to A times XS. So that we write down here, we got this gain is XO divided by XS. XS is the signal input. See, that's your gain. So that gain, we give it a name. We call it AF, called feedback gain. And from this equation here, we can derive it to be A over 1 plus beta times A. So this is our called feedback gain. So from this feedback gain, we have quite a few things we can discuss here. Now, for example, typically this A is fairly large. Now, this beta is not the gain of the BJT. Okay, so this beta is simply just a number. And this beta typically is small, like usually less than 1, and maybe even smaller, but it's okay. A is big. So beta times A typically is quite a large number, which means beta times A could be much larger than 1. So from here, you can see if beta times A is much larger than 1, we can neglect 1 here. And then this A will cancel. Therefore, your gain becomes, let me write down this equation here for you. We can have AF equal to A over 1 plus beta times A. So if A, beta times A is very large, means beta times A is much larger than 1, then we have AF equal to A over beta times A, which is approximately 1 over beta. And this is called, this is a feedback gain when A is, beta times A is fairly large. So this is interesting because the feedback gain, if A is large enough, the feedback gain has nothing to do with A. That's basically what it tells you. So this, you guys probably remember in 310, you learn op-amps, or 210, you learn op-amps. We assume that op-amp has a gain of like 8,000, 10,000, and fairly large, and then we assume it's actually infinity. So comparing to 1, that's fairly large. So we do that. So once you do that, that gain doesn't matter anymore. As long as it's large, the gain is proportional to the inverse of the feedback gain. It has nothing with actual amplified gain, but with the feedback gain. So this is why I say beta is typically less than 1. So if your beta is 1, your gain, loop gain will be 1, not loop gain. Your feedback gain will be 1. But if your beta is 0.1, what is your gain? It's 10. If your beta is 0.01, then your gain is going to be like 100. So that's what it happens is that your feedback gain decides, your feedback, that beta, decides what your total gain of your circuit. So that's kind of very important concept to understand. And then, okay, then you say, well, why do we need a feedback gain? Well, this is because later on we're going to demonstrate the feedback is going to help you to increase your sensitivity, increase your bandwidth, and improve your stability of your circuit. So this is very simple to understand. Now, suppose you have op-amp. Suppose you have Vi connected, then you have A equal to 8,000. And this is a typical number. You get VO. See, what happens is that if your input is 1 millivolts, how much would you get at the output? 8,000 millivolts, which is 8 volts. So you see, from 1 millivolts, you get 8 volts, which is good in terms of gain. But the problem is that a little bit of fluctuation in the input, let's say noise. Noise has 0.1 millivolts. How much do you get at the output? 0.8 volts. That's huge. So which means yes, you amplify your signal with a large gain, but you also amplify the noise. So ideally, what you want to do, I want to amplify that 1 millivolts, a dozen, that's good. But I want to suppress that noise to not 0.8 volt, but maybe 0.1 or even less. So your feedback can do exactly that for you. So that's why feedback is so important. Okay. So in the sense that for our future study, we just need here to have a definition called loop gain. So the loop gain is they break the output. They break the output instead, and then they form this like a loop. So you go from here all the way, you come this way, you just break it here. And then when you circle this loop, you get a gain, which is called loop gain, which is AL equal to beta times A. So this is called loop gain. So now you have 3 gains in a simple circuit. So we have open loop gain. You guys probably know what loop gain is, right? Open loop gain is, right? Do you know what open loop gain is in the circuit? That's A. And you have closed loop gain, or sometimes called feedback gain. But don't confuse this one with beta. So sometimes, I would prefer not to use feedback gain, because feedback gain sometimes can refer to the gain of the feedback loop. Okay, so let's just call it open loop gain and a closed loop gain and loop gain. The loop gain is the multiplication of A and beta, but closed loop gain is AF. Well, we already derived AF is equal to A divided by 1 plus beta times A. And this number is equal to 1 over beta, 1A is large. So that's the loop gain definition. So now we're coming down. Well, what I talked so far is still a block diagram, which you're learning in 420, if you have learning in 420. How many of you have taken class 420? Oh, not yet? Oh, you do? Okay, most of, oh, okay. That's great. Well, I mean, you guys are going to learn it later on. Say, okay, well, understand why you talk about this block diagram. So that block diagram is what you use in control systems class all the time. They rarely do circuit. Okay. So now here we're going to do circuit. So this is op-amp circuit with an input of Vs at the plus terminal, and we have this V out at the output terminal, and then we have this R1, R2, which connects to the negative terminal of the op-amp. So you might say, how do I know it's a feedback? How do I know this is a feedback, not just the regular amplifier? Well, in the future, you will notice that for a regular amplifier, there's no connection between output and input. Okay, so they basically are kind of decoupled by the amplifier, by the MOSFET, BJT, whatever multi-stage. So they're decoupled. But when you have a feedback in the input of your circuit, there is a connection between your signal and your output. So in this case, we can draw the equivalent circuit. I mean, if you know how to solve the circuit in 330, that's great, but you don't have to, because we're going to do it here anyway. So we are going to draw the equivalent circuit here. So the equivalent circuit is going to something like this. Or maybe, you know what, just for you guys' reference, I'm going to do it this way. I'm going to draw it here. So this is R2, this is R1, this is your Vs, and this is your A times, this is your A times Vi. And this is your VO. Okay, So if you look at the circuit, let me make sure I have the correct circuit for you guys. Yeah. So if you look at the circuit here, so you have A times VI, where VI is not a Vs. So now you understand why this is called feedback, because your output is proportional to A times VI, not Vs. But Vi is the difference between Vs and here. And let's call this one Vx. So how do you calculate Vi in this case? Well, we know that. Let's write down here. So Vi is going to be the difference between Vs and Vx. Okay, can you guys tell me how do we calculate Vx? How to calculate Vx? It's a voltage divider, right? So VO is on the top. So if I actually erase this, you probably understand better. So you look at what happens. So VO is divided between R1 and R2. So the voltage across R1 is what you want, is Vx. So we can apparently write Vx equal to R1 over R1 plus R2 times VO. You see, Vx is a function of VO, and Vi is a function of Vx. So therefore, we can say that we can plug in this, and also, of course, VO equal to A times Vi. So now you can plug in everything together to get what we wanted. Let's suppose. So I'll plug in this back to here, Vx to here and Vi to here. So let's derive it. So VO equal to A times Vi is Vs minus Vx, and Vs equal to Vs is there, and X is R1 plus R2 times VO. That's what we get, and then we'll move VO on the other side. So this we can extend this to A times Vs minus R1 plus R2 times A times VO. Now we can move VO on to this side. And then we get 1 plus R1 over R2 times A times VO equal to Vs. So we have now VO over Vs equal to A times Vs, okay? A times Vs. So A over 1 plus R1 over R1 plus R2 times A. Okay, so that's what we get for this gain. Now for this gain, again, if A is large, so and then we have VO over Vs equal to R1 plus R2 over R1. This is your AF. You probably sound familiar about this op-amp analysis you did before. Oh, the output is simply the R2 plus R1 over R1 times Vs. So we completely eliminated everything here. So now you guys can tell me now, if I draw the, let me see, yeah. So this is the equivalent circuit, and that's how let's write the gain here. So AF equal to R2 plus R1 over R1 times, that's it. Well, this equal to VO over Vs, right? So if I write that equation over, that's only if A is large. But if the regular equation will be A over 1 plus A times R1 over R1 plus R2. So if I do it this way, you guys probably know that if I do it this way, so this is Vs, this is Vi, plus sign, minus sign, and here is beta, and here is A, this thing here, this here. So what is beta now? Can you tell me? So A over 1 plus A times beta. So beta is really the ratio between R1 is between R1 over R1 plus R2. So that's your beta. So you see, this beta is definitely less than 1 in this example. Yeah. So most of the time, beta will be less than 1. And if beta is larger than 1, this circuit probably is not going to work. Okay, so usually, because otherwise it's a beta increase, decrease, it's too big, right? So that's what we have. So if we have this circuit, and we probably can get a bunch of examples to demonstrate the different circuits. Let me see if there's an actual circuit that I can show you. Feedback. For no introduction. Let me see if there's another example that I can show you. No, actually, there is no example. Okay, so we're gonna no example. We'll continue to the next section now. So the properties of negative feedback. There are quite a few, and it's analyzed in detail in the book. But I want to pick up the few simple ones I want to look at. First of all, we want to look at the sensitivity. Sensitivity means the change of output in terms of input. The example that I gave you guys earlier, if your input is 8 volts, and if your input change 10%, your output also changes 10% with the actual gain. So if you have a block saying any gain here, so you have Vs, you have Vo. So if this Vs plus delta Vs, your output will be Vo equal to A times Vs plus A times delta Vs. Vs means the small change of Vs. So the actual change, so delta Vo equal to, I call it Vo prime. So Vo prime. So this Vo is equal to A times Vs, right? So Vo minus Vo is equal to A times delta Vs. So now you see delta Vo over delta Vs equal to A, right? That's that's easy to understand, because your input change, whatever percentage, is exactly amplified at the output. So the percentage of change of input brings in the same percentage of change at output. Well, this again goes back to example. Your input is 8 volts, 1 millivolts, your output is 8 volts. But if your input becomes 0.9 volts, your output so if A is 8,000, just write down. And then your Vs is 1 milli, and your output is 8 volts, right? So, but if your Vs becomes 0.9 millivolts, your output becomes how many volts? 8,000, so 0.72 volts. So you can see the change again is 10%. Just want to illustrate. But for feedback, with feedback, we know the feedback gain, or the closed loop gain, is A times 1 plus beta times A. So which means if I take so if I take an input of Vs, my Vo will be AF times Vs, which equal to A times 1 plus beta times A times Vs. Okay. No, actually, I think I'm making some sort of mistake here. Yeah, no, this, okay, I can keep that there. So the second scenario, I want to continue with this. If A change to A plus delta A. So I want to illustrate also what happens when the gain actually changes. And this is also very important, because when you go buy op-amp, when they say the gain is 8,000, actually for the lousy op-amp that you buy for like $2 each, you never get 8,000. You might get 7,500, you might get 8,500, you might get 8,200, but you will never get 8,000. So when you do that amplifier, you can imagine that people doing this, getting this thing from you will be, the output will be all over the place, even for the same input. So what happens is with the gain is, so VO, delta VO is equal to delta A times VS. That's what we're going to get for the due to the gain change. The reason is that VO is equal to A times VS. So VO prime is A plus delta A times VS equal to A times VS plus delta A times VS and equal to VO plus delta A times VS. So delta VO equal to VO prime minus VO equal to delta A times VS. So this is the gain. So when delta A changes a certain percentage, your output also changes proportionally. So this is easy to understand. So now now we go back to, so this is number 1, this is number 2. Now we go to number 3. So we're going to analyze what happens with the feedback. So with feedback, we got this number here. So now let's say A changes from A to A plus delta A. So we're going to plug in this number here. We're going to have VO prime equal to A plus delta A divided by 1 plus beta A plus delta A times VS. And then this goes to A plus 1 over beta A plus delta A times VS plus delta A divided by 1 plus beta A plus delta A times VS. A plus delta A times VS. So you're going to see here, it's going to become really interesting on this expression because if you look at carefully, this delta A is a change of this A, which means delta A is a small number. So in this expression, we can basically neglect delta A over here. So if we neglect delta A here, this will become A over beta times A times VS. So what is this? Is VO. And this one, of course, we have delta A here and also delta A here. But ideally, delta A is small. So we can neglect delta A over here. So you have delta A over 1 plus beta A times VS. So that's exactly the solution we want to get, is that, let me see if I have the, let me do this. Oops. New slide. Okay. So I'm going to add a new slide so that I have the. So now we have current. Okay. So now we have this A. No, not A. Let me see what we have. What? Oh, what happened? Doesn't move. Let's do it again. I'll do it this way. So we have here, we have this VO prime equal to this one. As I said, this so this term equal to basically VO, and this term becomes the delta. So we're going to have VO prime equal to A plus 1 plus beta A times VS plus A over beta plus 1 plus beta A times delta A times VS. And so neglecting. So this is important because delta A is small so that we can neglect it. So here this becomes VO plus delta A over 1 plus beta times VA, beta times A, so beta times A times VS. So we got this one. So delta VO equal to VO prime minus VO equal to delta A divided by 1 plus beta A times VS. This delta A. So because beta A is large, therefore we can further neglect one. Therefore, we get delta A over beta times A times VS. So you can see now this delta VO, in comparison to the one that without feedback, the without feedback, what you have is delta A times VS equal to delta VO. So if you compare these two numbers, you will find that this number will be much larger than, much smaller than this number. You know, for example, if we have A equal to, again, we're going to use the next number 8,000, beta equal to 0.5. Let's get an example. So beta times A equal to 4,000. And if delta A is, let's say, 500, see what happens. If change 500. So open loop, your VO, delta VO equal to delta A times VS equal to delta I is 500. So it's 500 times VS. But for closed loop, you have delta VO equal to delta A is 500 and divided by beta A is 4,000 times VS. It's going to be divided to 1 over 8 times VS. So now you can see that instead of amplifying that input, by 500 times, now you're amplifying 1 over 8. That's really, really huge reduction in terms of sensitivity. So your output is no longer sensitive to the gain chain. So in this case, if you go by op-amp, you don't have to worry about it's 8,000 or 7,000 or 5,000, whatever. Use that number. As long as the number is sufficiently large, you use feedback, your gain is pretty much insensitive to that A. So that's very good property for feedback control. So that's number one. So now we're going to look at also bandwidth. So first, let me review. Do you guys still remember what bandwidth means, right? So in our previous chapter, we talk about the frequency response. We talk about high frequency response. We talk about low frequency response. And we have something like this. And in the middle part here is called bandwidth. So your bandwidth is omega h minus your omega L, basically. And the definition could be wrong in the book. But if you consider, your high cutoff frequency and your lower cutoff frequency, so the bandwidth is omega h or minus omega L. So that's for your bandwidth. So typically, for any amplifier, the larger the better for the bandwidth. But the larger means you have to use very expensive components. That's again for open loop only. Now, if we have a closed loop, we're lucky because we don't have to use expensive components, but we can have a much larger bandwidth. So why is that? Well, again, let's write this loop equations. Well, is AF equal to A times 1 plus beta times A. So previously, what we did is we think A is the middle band. Basically, we did not take about any frequency response. So in real life, you really have A equal to AM times this like J omega. Let's see how do they express it. S, yeah. So AM. So basically, what you're doing is you're doing this A is actually S instead. So which is going to be AM, which is middle band plus 1 over S over omega H. We're going to just use one example for the high frequency response, but we can certainly do the low frequency response as well. It's the same derivation. So S equal to J omega, as we all know it. This equation here and this equation here, those ones that we're going to plug in. So of course, there's a beta as well. So beta can be also written beta as a beta, basically just beta S, whatever that J omega is going to be. But in this example, we're gonna just simply assume beta is a constant. It does not have any phase angle. So therefore, we have AF. We're going to plug in this SO here. So we're going to plug in this A to AM, 1 plus S over omega H. That's the numerator. And the denominator becomes beta times A. M is middle band divided by 1 plus S over omega H. Okay, I'm going to manipulate this equation here by multiply 1 plus S over omega H on numerator and denominator. I get omega M. And here I get 1 plus S omega H plus beta AM. That's it, beta AM. Okay. So if I move this AM out, I can get 1 plus, let's see, 1 plus S over, okay. So so I get this AM plus 1 plus beta AM plus S over omega H. Remember, for the high frequency response, we need to get this down to like 1 to write in the form 1 plus S over something. So we're going to divide 1 plus beta AM on both numerator and denominator. We got AM plus divided by 1 plus beta AM. And then here we get 1 over, there's 1 plus S over 1 plus beta AM omega H. So I simply divide this on bottom and top. So I get this S over omega H. Now this omega H becomes this much. So you can see from this equation, you can probably got what it means, right? So the first term is F. The first term here is F for the middle band. And this is your frequency response. So basically, we can write down to 1 over 1 plus S omega F. And that's called feedback. So your omega F equal to 1 plus beta AM times omega H. So this is AM times omega H. So this omega F is a very large number because beta times M can be fairly large. Remember in the previous example, we have 4,000 plus 1 is 4,001. So if your frequency is whatever it is, now is amplified by 4,000 times. That's not like adding 4,000, it's multiplied by 4,000. So if your original frequency is say 1 megahertz, now it's 1 megahertz times 4,000 is 4 gigahertz. That's huge increase of bandwidth. So in the plot, if we want to plot the actual like frequency response, so you can do it this way. So if this is your original, and this is your AM, and this is your omega h, so what you're doing is you're amplifying this one to this much. So this is your omega h, but this is your A plus beta times A, 1 plus beta times A times omega h. So this is what you have. And however, remember, this is your 20 log AM, but this is your 20 log AF. So that this value, of course, is also smaller. The gain is also smaller. So now this feedback, apparently when you increase your bandwidth, in the meantime, you also reduce the total gain. But reducing total gain is not bad because we are increasing also our decreasing our sensitivity of our circuit, so which is a good thing as well. So that's why this is really important. And also the last section in this, the last subsection in this book, it talks about reduction in the nonlinear distortion. So basically, what it is you remember in our MOSFET, we have 0.2 volts when the transistor is in a saturation mode. When we use linear, so from VDS, it has to be something. It has to be larger than VOV over voltage, VGS minus VT. We cannot overcome that voltage, which means within that little range, we have some trouble to getting our system to work. So with this feedback, you can actually eliminate that nonlinearity due to voltage. So that's why these days, if you go buy op-amp, you can buy what's so-called real-to-real. So you probably know what it is now, real-to-real. Real-to-real means your output range is from minus VSS to. Well, this is interesting because in your quizzes, well, I asked you guys to look at the output range, and the output range is VDD minus the overdrive voltage of that top transistor, and the minimum voltage is VSS plus minus VSS plus the overdrive voltage of the bottom transistor. So it's always less than VDD and VSS. So that anyway, so just give you some ideas what it means. Okay, so we're not going to go to too much details of that section, and we can skip over, and then this we can move on to the next one. So let me see. What time is it? So you guys have any questions? So this feedback so far is fairly easy. And I just want to summarize for you. So the feedback gain is much smaller than the open loop gain. And if the open loop gain reduced down to only the feedback loop, the feedback gain, which is 1 over beta. Okay, so that's what your property you have. And the property of this feedback gain, it can reduce the sensitivity, which means your output wouldn't change very much. If your gain, open loop gain changes a lot, your output gain will still maintain relatively constant. And it can increase bandwidth. It can reduce the distortion at the low voltage output. So that's very good properties. And in order to, yes, okay, so this circuit, this drawing from the book, basically it shows the actual open loop gain and the feedback gain on the same graph. Basically, it extends to the omega HF here. There's little interesting, just to remind you, the M, they use this absolute value because M sometimes can be positive, sometimes can be negative. So this has to be absolute value. So even M is negative, yeah, it wouldn't reduce your bandwidth actually. It will still increase your bandwidth and increase your bandwidth a lot, 4,000 times. And 4,000 is how many decades in the example? 1 decade is 10. So 2 decades is 100, 3 decades, 1,000. So 4,000 increase your bandwidth by more than 3 decades, 3.5 decades, right? So when we talk about feedback, how do you get the output to be reflected in the input of your amplification circuit? It's very important. So I think probably today I will, what I will do is this. Okay, I'll do it this way. So this is a generic diagram, even though it's a generic diagram, but they got circuit component. So this is different from the block diagram that you will learn in 420. So that actual block diagram is actual circuit unit. Okay, we just didn't draw it. And the feedback can be also a simple circuit. So if you look at how the feedback is connected to the output, we want to like break down the circuit so that we can understand what it means. So if you look at the input to the feedback, we call the block, we call the 2, like node 2 here. So apparently the feedback to the feedback block is the same as your output voltage, right? So we drag the voltage all the way back to the feedback block. So this is why we call this one. It's called voltage feedback. So this is called voltage feedback. So, and further, if this is a voltage feedback, what do you say about the input to the feedback block and output? What type of circuit connection are they? In circuit connection, you know you have series and parallel. So what type of connection is between, what they call this one? VO here, and I don't know what they call this number, but let's just give it some sort of a symbol here. We call this one, we call this one, we call this VF1, doesn't matter. So what is the relation between VF1 and VO? You might say, oh, VF1 is equal to VO. But from the circuit point of view, so VF1, VO, or O. Okay, in other words, what is the relation between your basic amplifier and the feedback network? What's the connection between these two on the right hand? They're in parallel. They're in parallel. So we call this a parallel feedback, right? And they give this parallel connection a name called shunt. Okay, so in the future, if you see the word shunt means parallel. Okay. Now let's go back to the right hand of the diagram. Between the basic voltage amplifier and the feedback network, how are they connected? So if you go from VS, you go RS, you go to the voltage feedback, and you go here, go to feedback, and you come back. They are in series. So this is called series feedback. They didn't give series on a different name. Okay, that's good. So in the sense that your feedback, the output of your feedback network is connected to in series with the input voltage. So in other words, we can know that Vi equal to Vs minus Vf, because this Vf, right? So yeah, so it's in series, they're in series. So naturally, so we call this one series shunt. So we call it series shunt, maybe this. So the input side is series and output side is shunt. So this is called a series shunt feedback. So mathematically, you might already know, oh, if you have a series shunt, I can similarly build shunt series, series, right? You can do that. Why not? Right? So that's what it becomes more and more complex in the book. And we want to get you to at least one of them, how to analyze it. So from here, I can give you example of voltage feedback with a series shunt. So sometimes it's a little bit difficult by looking at the circuit to understand whether it's series or whether it's a shunt. So luckily, not all, unfortunately, you guys have to identify this type. Series or shunt connection, I give you a circuit. So in the exam, I'll give you a bunch of circuit, and you're going to tell me which one's series shunt, which one is series, which one is shunt, or shunt series. So 4 different types. Because input has series and shunt, output has series shunt. So 4 different combinations. And you have to be able to identify which one is series, which one is shunt. So take this example. How do you know like this is a series and shunt? Well, what you can do is like what the book is did. So you put this as a block, like a feedback as a block, and put this as another block. So now you redraw the circuit. You redraw the circuit. Okay, so this is a block, and this is your input. And over here, and we are connecting to this basically block. And here, we have here going up. Let me do this. Going to here. Okay, this is your VO. Okay, so it is still not that clear to see the bottom block. Then I replace the blue part with the block, and the top is connected to the actual amplifier, and the bottom is connected to ground. So this is still a little bit tricky. So in fact, in order to make it easy, because this line, I can move this line to anywhere, right? And this line, I can move this line. And also, the output does not have a ground. So I'm going to have a ground. So actually, the ground is coming out of this way. So actually, this is your ground. So I just put it right. But this has to go a ground. So I connect this to a ground here. So this way, I actually have a circuit that I can redraw again. Let me remove all these things so that we don't mess it up. And redraw this one, okay? Redraw. This is your output. It's ground. And apparently, there's a ground over, is VO. So I'm going to redraw the circuit to this block here and this block. I'm going to redraw this one instead. I'm going to draw the ground. I just move this a little bit. So this one is connected to here. Now, the ground is apparently something that we can always connect. Like here, we can connect this one to ground. because ground is ground, right? So, and this way, you see this is VO, this is VS, this is VI, this is your beta, this is your A. So you can see now, so the output is actually, so we can connect, if we connect this like this, it becomes, output becomes parallel, input is series. So this is series and parallel feedback. So if we, so I'm gonna duplicate slides. Oops, I didn't want to duplicate slides. I want to add a slide, a new slide. Okay. So I want to add another new slide, and we can get it done today. Okay. So from person view. If we will recall I want to recall the series parallel feedback. Apparently, I mean, you can connect a lot of ground. It doesn't matter as long as you connect those outside to ground. So this is your series shunt. So similarly, we can, if we can build a circuit that says series, how would you build it? So which means the input side is going to be the same, right? So that doesn't change. But by definition, our output is going to be in series. How do you make the output in series? Well, we can do the same thing, just like what we did here. In series. You see? The output, we all going to the block and it goes to there and going back. So that's series. So it's so fairly simple. Series. And we can then do shunt. So we can do this. So we know the output is shunt. So we're going to do this one first. It's better. Because it's a shunt, right? So you probably already know how to do it. This is your input. And because it's shunt, which means the feedback block is connected in parallel with the input. See? This and this, they're in parallel. So this is your input. So this is called shunt and shunt. The output, oops, the output has a mistake. Don't make that mistake. Mistake here. So guys, if you guys see I make a mistake, let me know. Okay, if you identify, then we'll correct it. Okay, it's okay to make mistakes. That's why I give you guys partial credit when you guys do the exams. But we just need to know and we correct it. So, and then we had a series, we had shunt, series shunt, and then now we have one more. We need a shunt series. So for shunt series, apparently we can do from here to here. So the input is like here. Because this is a shunt, so we do it this way. But the output is series, and it goes like this. Okay, so that's your shunt series. So here you got 4 different amplifiers. We could actually go into each one of them to analyze the feedback, the gain of the circuit. So for example, we can take so we have series shunt. Maybe we can take the shunt series example to see how if we can get the gain. So let's take the shunt series example. We're gonna shunt series. I mean, we can do anyone, right? So we take the shunt series. So that's why I'm not going to go to every. I'm not going to go to every type to tell you how to do it. We're going to just go in through a few examples. So shunt series means A, VI, VS. Your feedback loop, this is better. Output is series, so we put it in series. Oh. So how do we analyze a circuit like this? Well, first of all, you need to get a number of different symbols. We're going to call this one Vx from here to here. We can from here we call V F in, and we call it VFO. VF in, okay. And then this, of course, is Vs because the same as Vs. So nowadays we can do what is Vx? We can identify. So Vx equal to Vs is input times A. So it's A times Vs. And what is the Vf in? Vf in is equal to, or in other words, Vx plus Vf in equal to Vo. So Vf in equal to Vo minus Vx, right? So, or you can write Vo equal to Vx plus Vf in. Okay, and what is Vf? What is VFO? You guys tell me. VFO is the output of the feedback block, feedback network, which means it's beta times VF in. Okay, and but VFO also equal to, you see, VFO and VS they're in parallel, so it's also equal to VS. So nowadays we can plug in. So from this equation here, we can get VF in equal to Vs over beta. We get this equation over here. Now we plug in Vf in over here. So we have Vo minus Vx equal to Vf in equal to Vs over beta. So now we have Vx here, we can plug in again here. So Vo minus A times Vs equal to Vs over beta. And then we're going to multiply beta on both sides. We'll have Vo minus beta A times Vs equal to Vs. Is it right? Vo equal to, so Vo minus Vx equal to V in beta equal to Vf in. Vf is Vs over beta, Vs over beta. Okay, Vs over beta. So Vo minus A times Vs. Okay, and multiply beta. So we got this. So then we have Vs. We have beta times Vo equal to 1 plus beta A times Vs. Vs. So from here, we're going to get F equal to Vo over Vs equal to Vo over Vs, Vo divided by Vs. So 1 plus beta A divided by beta, which equal to 1 over beta plus A. You know what? I don't think this is correct. We have made a mistake somewhere that I need to fix. The feedback definitely cannot be like this. So Vx is A times Vs. The Vf in is Vo minus Vx. So Vf in is Vo. So Vfo is beta times Vf in Vs. So Vs equal to, so Vf in equal to Vs over beta. Vo minus Vx. Vx to A times Vs. V times, it's supposed to be the other way around. Somehow, look like I made a mistake somewhere. Apologize about that. Let's see. Series parallel. Oh, I see. Okay. So we'll redo this next time because I should have done with the current gain instead of voltage gain. So voltage gain here, because it's in series, the output is supposed to be so this is wrong. Okay, so don't take this. Well, you find the current gain, which is the AF, is going to be same thing. It's going to be beta 1 plus beta A. That's going to be gain, but this F is IO OIS instead. So this F. So that's instead of voltage, we're going to take an input gain. So I made a mistake here. So when the input is the output is in series, they do the current feedback. It's called current feedback. So you have to get current gain, not voltage gain. So we're gonna look at this into a little bit more next week. And with that, I think we can, yeah. So there are two more examples that we can look at. Basically, for this one, you can see what type of feedback is this going to give you? Well, your input is here, and your feedback is here, but your gain at RD1 over there is proportional to VGS. Then VGS is the difference between VS and VF. So your input is series. Okay, and your output is VO over here, and your VO is dragged back because the current here is fairly, if it's fairly small, this two becomes parallel series. So this is a voltage divider. But it's not strictly voltage divider, but you can think about the voltage divider because there'll be something over here, but it's kind of voltage divider. So therefore, the feedback is the output is a voltage feedback, which means it's series short feedback or voltage feedback. So that's this one. And the next one is basically same thing. And you see, this is the common, this is like a common drain. This is the input at the source. So this is a common gate amplifier. But instead of using the common gain amplifier, your input, your output is VO, okay? But your output VO is divided between, again, R2 and R1. So this is a voltage divider. So your output is a voltage. So it's a short. And your input is the VS is coming here, but what your output over there is proportional again to VGS. So VGS means it's the difference between this one and this one. So VG and S. So your output, your input is the VS, but the difference between VGS is this one and the voltage of this one. So your voltage is not directly. So your input is series. You see, this is a series block. So input is series, output is parallel, so it's a series parallel. So this is series shunt. Or sometimes it's called voltage amplifier, voltage feedback. Basically, you're taking voltage, this is same thing. So this one is the same. So it's a voltage feedback, and it's also series shunt. Okay. So with that, we're going to conclude the lecture today. I'll see you on Wednesday. Good night. Yeah, you can pick up your quiz. Yeah.
Crazy. This looks more like a PMOS, and this looks more like an NMOS to me, and as like the schematics. They look backwards.
So we didn't talk too much about it. Actually, the PMOS, we did mention it, but we didn't go into too much detail. But let me show you. Let me quit this. That we don't record anything.